Okay, so here we have a series 1 over e to the n plus 1 over n times n plus 1. And this one's fun because, as you can see, I've already done this here. We have to split it into two different series, into two different sums to get the entire series and just add them. So the form here is the same, and we're going to be adding them. So let's start with this side. Let's start with side A. We're going to call this A, we're going to call this side B, or side 1, side 2, whatever. How do we actually work with this? Well, we can notice we have something to an exponent, and this is going to be a geometric series. It's going to be a geometric series because this is the same as e to the negative n. You know, you have something, you're taking it to an exponent. Whatever's inside that's being taken to some exponent, that's the common ratio. In this case, our common ratio is 1 over e. It's 1 over e because notice that these two statements are the same. If you take 1 to any n, it's still just going to be 1. So you could totally do this. So this is how our geometric series looks. We next ask, with a geometric series, is the common ratio less than 1? If it's less than 1, this converges to something. Is this less than 1? 1 over e, obviously, is less than 1. You're dividing 1 by something. By definition, it's going to be less than 1. So this is going to converge. This is certainly going to converge here. What's it going to converge to? Well, we have a formula for that. That's a over 1 minus r. What is a? We know what r is. R is our common ratio. So that's 1 over e. A is going to be our first term. What do we mean by our first term? We plug in 1 because it's given here. N equals 1. We plug in 1 right here. We get our first term, which is going to be 1 over e. So this is what it converges to. I'm not even going to simplify. I'm just going to leave that. So that's what we have over here already. Now we just need this side. With this side, it's going to be a little more involved because we've got here in the denominator a factor. We've got n times n plus 1. So whenever you have that, if you remember from previous sections, we're going to use partial fraction decomposition. And, you know, some people like it, some people don't. So we got a plus b. We got a and b, not bx plus c. We would have bx plus c if we had something squared, but we don't. We have two linear factors. So in other words, it's the power here is to 1. You've got n, and you've got n. So you don't have n squared or something. So that means we've got a plus b, not a plus bx plus c. And so a and b are what are going to give us 1. So we got a over n, and we've got b over n plus 1. These give us 1 over here. If you're going to add a and b, they're automatically going to have to give you 1. So then we multiply. We cross multiply here. We get bn. You could do, some people like it one way, some people like it the other. You could do bn or nb, and you also multiply this, a times n plus 1, and that would give you bn plus an plus a. Then you get everything together that has an n. A plus b both have an n, and the a is the only one that doesn't. So now that we have this, we look at our original thing and we see, oh, was there any term that had an n in it? Was there any term that had an n? There isn't a term in there that has an n. So that means that a plus b must be 0. A plus b equals 0. What is the other term? The only term in that numerator is 1. And the only constant here we have, which is not multiplied by n or n squared or anything else here, is a. So a must be the one that equals 1. Because remember, when we add these, we need to get 1. So a equals 1, and therefore b equals negative 1. b equals negative 1, because 1 minus 1 is what would give us 0, and we knew that a plus b had to be 0. Okay, so that's how we do the partial fraction decomposition. Now we just plug in those numbers back up there. We got a 1 and b equals negative 1. a 1, b equals negative 1. So now we have our two little sides of this. When we have our two little sides, and we have this in a series, this is what's going to happen. We've got this series. We could change this with this now. We've got 1 over n, and we've got minus 1 over n plus 1. We're going from 1 to infinity. And now I encourage you to think about this for a moment, because what would we do here? What could we do? Well, we could plug in terms. We could plug in terms. If we start plugging in terms here, because that's ultimately what we're going to infinity, but we have to look if something cancels out. Perhaps once we have something of this form, when we have a fraction here and a fraction here, we can start asking, we plug in 1, we plug in 2, we plug in 3. Do things start to cancel out? Do we reach a sum? That's how we find out. That's how we find out, by actually plugging in things and seeing if things cancel out. People call this telescoping. So with our first term, with our first n equals 1, we would have 1 over 1 minus 1 over 2. And this would be when n equals 1. And with the series, we're adding stuff, right? We're just adding stuff. So then we would have n equals 2. With n equals 2, we would have 1/2 minus 1/3. And then we would have n equals 3. n equals 3, and with that we would have 1/3 minus 1/4. As you can see, stuff is canceling out, and it's going to keep canceling out. Like, this cancels out with this, and this cancels out with this. And if you keep going and keep going and keep going, they're all going to keep canceling out. The negative 1/4 is going to cancel out with a plus 1/4. It's going to keep repeating that same pattern. So the only thing we're left with, really, is the first term, and then we have to see what happens way at the other end. So how do we find out what happens way, way, way at the other end once we've added so many? Because everything seems to be canceling out. What happens at the very end? At the very end, we have 1 over n minus 1, right? Because that's like 1 less than just plugging in n. So that's what's going to tell us the behavior at the very end. We have negative 1, and then we've got n minus 1 also instead of n. And so this is when we plug in n equals n minus 1. So we were plugging n equals 1, n equals 2, n equals 3, stuff was canceling. Now we're plugging n equals n minus 1, and this happens. I'm going to get some room, so I'm going to rewrite this up here. This is something which we found out for this, what that sums to. So I'm going to delete this. And now, what's the next term after this? What's the next term that we're adding? Well, it's just literally this. It's just 1 over n minus 1 over n plus 1. This is when n equals n. So now we could just observe what happens. We can observe what happens. And we see that stuff is still canceling out, because we've got n minus 1 plus 1, that's 1 over n So we've got negative 1 over n plus 1 over n. So everything cancels out. This cancels out, and we can assume that this also canceled out from the previous one because it's following the same pattern, right? So everything here cancels out except for that very last one. Except for that very last one, which is negative 1 over n plus 1. But remember, with these things, we are taking the limit as n approaches infinity. So what we have is, this is how it looks like. If you just got the first term with this telescoping, and you've got the last term like this, and then we take the limit as n approaches infinity, what's going to happen? Well, this is going to go to infinity. We're going to plug in infinity here. This goes to 0. We're subtracting 0 because we have 1 over infinity, which is going to 0. Limit as n approaches infinity 1 is just 1. So 1. All of that to show that this sum, our second sum, this one here, goes to 1. So that's how it looks. We're going to add 1. Add 1 here, and that's our final result for the series.